In today's lesson, we're going to take a look at standard L2 induction. And what induction is, it's the process of using magnetic fields to cause currents to flow in conductors. Michael Faraday was the first person to demonstrate this, so he showed that you can cause current to flow in a conductor by using and interacting it with magnetic fields. And he called this EMF. EMF is an alternative to us describing voltages. So when we talk about voltages that are causing charges to flow, EMF is just a voltage that develops when you have a magnetic field that's the source. So it's called electromotive force. And just remember that when we talk about conductors and we talk about currents, there has to be a conductive path, a circuit for the charge flow. So if we're going to induce induction in a circuit, we have to make sure that we have a conductive path for the charge to flow across. When we talk about EMF, when we talk about induction, there's two methods by which we can incur or induce induction. The first thing is that we can move the magnetic field source in the circuit relative to each other. So if there's a change in motion between the two, that will vary the amount of magnetic field that's acting on the conductor, which will give us a varying magnetic flux, and this causes current to flow. The other thing you can do is you can change how much the magnetic field strength is. But in both those scenarios, there's some difference in the magnetic flux that's acting on the circuit, and this difference in flux is what causes current to flow. Michael Faraday had an equation that he used to identify what magnetic flux was, or how magnetic flux related to EMF. And what he basically said is that if you change the magnetic field or the area over which it's acting on, it's going to induce some voltage referred to as EMF. And he related it, saying that the voltage or the EMF that's developed is equal to the rate at which the magnetic field strength is changing, or the magnetic flux is changing with respect to time. When we talk about Faraday's law, one thing that we have to keep in mind is that we can relate the EMF that's developed on a conductor to the electric field strength that's acting on the conductor. Charge always is going to reposition itself so that it has a zero electric field within it. So if you have a EMF that's acting on a conductor, it's going to cause charges within the conductor to relocate themselves. So we can relate Faraday's law not only to the change in magnetic field strength or the magnetic flux with respect to time, but we can also look at how an electric field acting upon them is going to be causing this change in voltage. So we have these two equations. It's the full length of Faraday's law that you see in your reference tables. Let's go ahead and do an example of this. In this example, we have a square conductive loop that has sides 0.25 meters long, and the loop itself has a resistance of 5 ohms. We place this in a magnetic field that has a change in flux that is negative 4 Tesla seconds. So this is telling us what the rate of change of our magnetic field strength is. We want to figure out what is the magnitude of the EMF induced. Well, when we talk about the EMF, that is the magnetic rate at which magnetic flux is changing over time. We have an equation that is showing us the rate at which the magnetic field strength is changing. So to get the flux, we just have to multiply this change in magnetic field strength by the area over which it's working at. So we'll expand this change in magnetic flux with respect to time to say really change in magnetic field strength with respect to time times the area. In doing that, we're going to find that we have a EMF of 0.25 volts. Now this is going to act as a voltage, so if we want to figure out how much current is circulating, we're just going to use Ohm's law, which is voltage is equal to resistance times current. We have our voltage of 0.25 volts, we have our resistance of 5 ohms, and we find that our current is 0.05 amps.